Okay, this is BiOS CFD, a series of short video tutorials on using open source software to do computational fluid dynamics for biological systems. This second lesson is going to focus on generating a computational domain with the snappyHexMesh utility as part of OpenFOAM. Last time we learned how to set up an OpenFOAM case and understand the case structure and build a background mesh with the block mesh utility. So here's a pic on the right. The screenshot kind of shows where we left off before. We have our background mesh that completely encased our geometry of interest, and now we're going to learn how to take that geometry of interest and turn it into a mesh that we're going to interact with the fluid flow solver with. So instead of having a box on the outside of the stuff, we'll have a mesh that's just exactly the shape on the inside. And for the purpose of this tutorial, we're going to mesh the inside of this structure, but you could also mesh the outside if you wanted to instead. So to do this, you need to upload your surface geometry files, and usually you use a stereolithography or an STL file. So you want to use some sort of file transfer software. CyberDuck is great for Macs. WinSCP is great for a PC, and hook that up to your system. If you're working on a domain, or what am I trying to say? A cluster that's off your home computer. If you're working on your home computer, on your terminal, you don't have to do this step. But these files need to be in the tri-surface directory, which is inside constant. So here, I'm going to look at my system and get these 4 STLs that I want and put them into the tri-surface directory. Let those things upload. Shouldn't take too long as soon as it gets started. Okay, about 30 seconds. So that while those are uploading, we'll go on. So snappyHexMesh is largely driven by the snappyHexMesh dict directory. So meshing a domain with snappyHexMesh is a little bit complicated, but there's only a few things that you have to change if you're just using this for a similar internal flow. You need to have a snappyHexMesh dictionary file, which is going to be in system snappyHexMesh dict. You need to previously have that background mesh from block mesh that we already made, and you need to have the service files to mesh from. So basically, these pictures on the right kind of show how snappyHexMesh works. This gray bigger box is a two-dimensional version of your background mesh that you had, and the outline of the car represents the outline of the service files you're uploading. And snappyHexMesh will take that file, those edges, and refine the number of meshes. So split the mesh elements that are near your edges to kind of get the detail of the shape. And then it will get rid of either the mesh on the inside or the outside, depending on what you want to do. So this illustration is for somebody that wanted to look at the aerodynamics of a car. So they care about the air flowing outside the thing. And we're going to actually keep the stuff on the inside and not the outside. And the last step is it'll take these edges and try to snap the final edges to the surface. And that's why it's called snappyHexMesh. So you have to make a couple decisions when you do snappyHexMesh. One, what kind of refinement? Do you want to refine a whole region? So do you want to draw a whole box around here and say, we're going to refine this whole region away a lot and get a whole bunch of little boxes in there? Or do you just want to refine the shape around the surface? So that's something you can choose. In this tutorial, we're going to do regional refinement. The degree of refinements are how many iterations of splitting these original elements into smaller elements do you want to do, and that'll result in a higher refinement will result in more mesh elements. Will be more finer mesh and more accurate, but will be computationally much more expensive. And you also have to decide with this step the names of the patches of your mesh. So every part of your mesh is going to get a separate name as you can choose it, and then that name is going to be a patch that goes through your whole simulation. It's going to have separate boundary conditions and everything. So choose wisely. Okay, so let's get a sense of what I'm talking about even. So if we look in my case directory, inside system, it's going to be a file called snappyHexMesh dict. Let's open that one up and take a look at it. There's a lot in here, and for the purposes of this tutorial, we're just going to change a few simple things, which is a section called geometry. This is where we're going to tell it every one of the names of the STLs we've uploaded and the names of the patches that they're going to go with. So I uploaded 4 STLs. I uploaded one called Farfield, one called Primitive Bronchus, one called Trachea, and one called Transition. So I need to tell snappyHexMesh about these files. So this first one here, left to scale, that's from an old simulation. I don't need that anymore. Let's call this one farfield.stl, pointing to that STL here. And I'm going to, the mesh patch name that's going to be made in that region, I'm just going to call it Farfield. Okay, the next one is going to be Primitive Bronchus STL, and I'm just going to call this Bronchus. Whoops. The next one is going to be called Transition.stl, and the name is just going to be called Transition. So here I'm telling snappyHexMesh which files to look for and what to call the patch name that it makes from that spot. Trachea.stl, just going to be called Trachea. Okay. Now again, I said we're going to do region-based refinement. So what I've done already is told it that there's going to be 1, 2, 3, 4 files here. And what I want to do is actually in this simulation, I'm going to make a little box around this bronchus region because that's where I care about the air flowing. And I'm going to refine that region a lot compared to the rest of it. So this refined region, I'm going to make a searchable box. And it's kind of going to work like BlockMesh did. Except BlockMesh was the whole geometry that had all the patches in it. But right now I'm just going to make a box around the patch that I want to be really highly refined. So to do that, I'm going to look in my paraview and get on my local machine that I was working on the last lesson with and just highlight the primitive bronchus and then make an X, Y, and Z that will encompass only those numbers. So the X minimum here has to encompass this negative value. So this is going to be negative 0.33 to, and the maximum with there would be negative 0.04. For Y, need to go from 0 or negative 0. Say 0.02 to, I'm just kind of arbitrarily getting a little bit of space around my mesh, and Z all the way from negative 0.42 to 0.56. And again, I'm making a box that will encompass just this STL that I want to have highly refined, because that's where I want to really look at the fluid simulation. Okay. Now I've got these 4 regions. I've got bronchus, trachea, farfield, and transition. I'm going to go down to the next section, refinement parameters, and keep going until I get to surface-based refinement. And all I'm going to do is replace these names with my new names here. So this one was bronchus. There was a trachea, farfield, and this one can be transition. And region-wise refinement. So you'll notice the stuff that says levels. This is kind of the levels of refinement. So what I'm telling it here is at the bronchus, I want you to refine 2 levels. So take this original mesh cube and divide it in. That would be level 1 refinement, and level 2 refinement would be this. So it refines it once by splitting it, and then it splits each one of those other things the next level. So we're going to do a minimum of 2 refinement and a maximum of 2 refinement at the bronchus and at the trachea. We don't worry about the far field and the transition. We can make this 2 to be consistent. But this is really going to be overridden by the fact that I'm telling it for this whole region, one that I made up here, this whole box that I drew around my region of interest, that bronchus, this whole box here, refine region 1. I'm going to turn the refinement all the way up to 1 times t to the negative 15 as a maximum, and 2 is a minimum. Okay, so it's going to really refine that thing. Now the only other thing we need to tell OpenFOAM or snappyHexMesh is whether to keep the inside or the outside of the mesh. So here the guy wants to keep the outside, but what we want to do is keep the inside. So we go in, there's a section called mesh selection, and it says location and mesh. So whatever point you pick, whether it's on the inside or the outside, will determine whether the inside or the outside is kept. So since we want to keep the inside, we're going to pick a spot inside the mesh. To do that, we want to go back into ParaView, and I think the easiest way to do it is to kind of get a slice, and you start out, your slice will be in the X direction. Okay, so that in that X direction, it's inside the surface, and then we'll switch it to Y, normal, get it kind of inside that surface here, and then Z, I'm going to move this so it's inside. So the X, Y, and Z coordinates are all inside, and if I hit apply, I know I'm inside that box. So I'm going to take these numbers here and move them into my snappyHexMesh file. So we'll do negative 0.192. We don't have to go to all the decimal points. 0.1794 and 0.421. Okay. That's all we've got to change in snappyHexMesh dict. So I'm going to hit escape, W quit to write that file and quit. Okay. Now I want to make sure that the snappyHexMesh is all that it needs to work. So I'll go back up to my case directory and just try to run snappyHexMesh right here in the command line. And it's starting to do things. It's working. So I'm going to quit that right away with Control-C to stop. The reason I want to quit it is because snappyHexMesh is going to take a really long time. It's a complicated thing for the computer to do. So it's better to actually decompose the case into a bunch of different processors and run it on those decomposed cases. And that's the advantage of using a high-performance cluster, is instead of using just one CPU, we can use 16 or 32. So here's kind of the theory behind this. You have some problem which is has 4 steps. And instead of asking the one computer processor to run that whole problem, we can break it up into a whole bunch of different problems and send them to different processors. So you need to kind of decompose our problem into multiple problems. And OpenFOAM has a utility that can do that called decompose par. And no surprise, it's run by something called decompose par dict for dictionary. There's multiple methods for decomposition. We're going to just use Scotch, which is already in there, and the number of subdomains has to be equal to the number of processors you're going to use. Every cluster is different. For this, we're going to assume you're using a 32-node processor because that's what we're commonly using in the lab here. So that, because it's a dictionary file, it's probably in system. There it is. And we're going to go vim decompose par dict and go down to our number of subdomains and change this to 32, write and quit. Now I can run a decompose par command, and it's going to think about that for a little bit and hopefully generate 32 processor directories. So each one of these directories now is going to be the instructions for a single one of the Okay, so now that we've done our decompose par, we understand how it works. We've got 32 processor directories. We need to understand how OpenFOAM is going to use those directories together to do a job. So the thing we need to understand is something called the slurm file, and batching. So this is a file that tells the software that controls the parallel jobs what it's got to do. And on the right is a screenshot of one of these slurm files. There's a bunch of different sections to it. The top sets up the environment. So what part of the supercomputer or the high-performance cluster we're going to use. How long are we going to let it sit there? How many tasks are we going to do? For now, we're going to try to keep it simple. The only thing you're going to change is the number of tasks. Make sure that that number of tasks, 32, is the same number of processors that you made in decompose pardict. You also need to set the correct directory where you want the job to happen. So here, set environment. We're going to set a working directory. For me, it's home and then OpenFOAM and then meshing tutorial. It's going to be something different for you depending on where you are. You can find out what your directory is by just doing a pwd, which stands for print working directory, and enter, and it'll tell you. So here I'm at home, then my unit OpenFOAM meshing tutorials. So here, this $home points you to your unit, and then after here is where you'd have to add that if you had something different. Then number 3, we have to source OpenFOAM. That's what this stuff does down here. Just leave that the same. And then number 4 is running the actual jobs. So the one in the middle where it says MPI run number processors NP32, blah, 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 snappyHexMesh, that's what we're interested in. And we're going to tell it to write the results of that. Normally what it would print out on the screen. So if we had just did snappyHexMesh here, this information that it would just be printing at us, we're going to tell it, I'm going to quit that, tell it instead to make a log file that contains that information. Now, you might notice that before I have the snappyHexMesh, I also have decompose par, and noting that into a log file, and then at the end, reconstruct par mesh. What that's going to do is after snappyHexMesh is done on 32 processors, it's going to reconstruct it so we can look at it. And since decompose par is already here, it's going to do that decompose par step. So we did it manually before and we ran up with all these processors. I'm going to go ahead and delete those. You should do the same thing if you did them. With this command rm for remove, and then -rf will allow me to destroy directories. And then pro star will be anything that starts with pro. So we don't need these directories because it's actually going to make them in our slurm file. So if we go ahead and look at that slurm file, which is here, snappyHexMesh.slurm, we've got 32 processors here on this line. We've got our working directory. That's what you want to change if it's different for you. And again, this 32 is the same as it down here, 32. 32 processors to do snappyHexMesh in parallel. So for now, you can just run this just like it is. And there's differences if you run on a different cluster or whatever. Whoops. I made a mistake here. Escape : WQ. Okay. Now that I've checked to make sure my batch file is the right one, I'm going to actually batch it by doing sbatch. S stands for slurm, so I'm using the slurm software, and batch is the command, and the name of the batch file, snappyHexMesh.slurm. And it tells me, when I've done that I successfully submitted batch job 19262. So there's a lot of jobs on CHBC all the time, or whatever cluster you're using. And if you want to check the status of your job, you can do S again for slurm, and then the command Q, which is like a list, right? And then search by unit, U0847231. That'll be different if you're not me. And hit enter. And you'll see I've got a bunch of jobs running right now, and one of them is 19262, which is here, snappyHexMesh. It hasn't started running yet. It's waiting on priority. So I'm going to stop the tutorial for now, and we'll catch up once it's completed its run. Okay, so we're back now after snappyHexMesh has run in parallel. So if we list our directory, you see we still have all those processor directories. And if we go inside of one of them, we see we actually have some new time steps. We started out just having constant in there, and now we've got also 0.005 and 0.01. This might confuse you because we're not doing any time step stuff, but the way that snappyHexMesh works is it saves the data in time step directories because it's kind of piggyback off of the rest of the OpenFOAM code, which is meant to work in time-step directories. If we go back to the case directory, we have 0.01 reconstructed. And the reason that that is reconstructed is because in our Slurm file, and the last thing, after asking it to run snappyHexMesh in parallel, we said to reconstruct par mesh at the latest time, so the most recent time, and that's 0.01. And what that is going to have in there is actually our completed mesh. We can check this by visualizing stuff in ParaView. So we'll pull up ParaFoam, and if we go to Apply, hit a surface, and we go to actually surface with edges. At time step 0, we have our original block mesh. And if we go to the next time step, 0.01, as soon as it loads, you'll see we have something quite different, which is the shape we asked for. So snappyHexMesh has taken that block mesh, refined it, and then gotten rid of the cells that were outside. And you can kind of confirm that it did this correctly by maybe taking a slice through our model. I'll do one on the z-axis. Kind of pick a fat spot there. Hit apply, and I can zoom in on that spot there, and go to surface with edges and see that we've got a bunch of mesh elements inside. So our new mesh domain is just the shape we're interested in, and now we're ready to kind of apply boundary conditions and do some fluid stuff. I'm just going to take a second now to go over a few quick things about Slurm files. So we've got a bunch of files here, and you might be kind of overwhelmed at first. This one over here, the one that ends with .slurm, that's the instruction Slurm file that we gave to OpenFOAM to do snappyHexMesh. This slurm hyphen and then the job number out file is the output from the Slurm scheduler. So we can look at that one, and it'll just say a bunch of information about what we asked for, like 32 tasks per node. We asked what thing to put it on, and there's no errors on here, but sometimes if things fail, there'll be errors here, and it's the first place you want to look. There's also going to be a node file, and that has information about which node we use. So we use 32 processors on the same node here. And there's also going to be one called logfile.snappyHexMesh. And if we do more command, that'll allow us to look at the log file one line at a time. And this is essentially all of the information coming out of snappyHexMesh. And instead of getting it printed onto the screen, it got written into this log file. So snappyHexMesh is doing a whole bunch of different iterations of snapping and iterating the mesh. And you can look at the details of that if you want. And again, if we go all the way to the bottom, there won't be any errors, but sometimes there are errors, and you need to read those error files and understand what went wrong. There's error outputs. In the bottom, it'll just say finalizing parallel run, which means it's finished doing the thing in parallel. We also have a log file from decompose par, which was the command, or the command that OpenFOAM used to break in the information into these processor directories, and then reconstruct par mesh to put them back together into this 0.01. Okay, so we have successfully run snappyHexMesh and generated a computational domain to do our simulation. The only thing that we have to do now is move the mesh from this weird time step into the constant directory where it should be for the rest of the simulation work. So if we go into constant, there's one here already called polymesh, and that's actually the output of the block mesh file. That's not the output of the snappyHexMesh file. So what I like to do is save that mesh as polyblock in case I ever need it again. So I'm going to use the copy command and recursive for a directory, and take this polymesh directory and copy it to a new directory called polyblock. If I list, I'll have polyblock and polymesh, and they'll have the same thing in them. And then I'm going to remove the polymesh directory, and I'm going to replace it with the one that's inside 0.01. So there's a polymesh in there, and that one is the output of snappyHexMesh. So I'm going to copy our recursive, this polymesh, and I'm going to move it up into constant. And I can now confirm that that one is there. And now that I've done that, I can actually delete my time step directory, the new one, and all the processor directories. Now I have in my constant a polymesh, which is the new thing. And if I go in there, I've got a whole bunch of files. The one that's important for you to look at is boundary. The boundary, you're going to have 5 domain boundaries, or 5, I guess, mesh boundary patches. And remember, these trachea, transition, bronchus, far field, those are the things you specified in snappyHexMesh dict originally. And they'll tell you how many faces each one of them has. The first one is called box, and that's left over from block mesh. We actually want to kind of turn that off because we're not going to use the block anymore. So what I'm going to do is comment out this whole section. If you use 2 backslashes in a row, it tells OpenFOAM to ignore those lines. And then I used to have 5 of these patches. I'm going to change it to 4 because I blocked out the box. And then write and quit that. And now essentially I have completed the meshing step of my simulation work, and I have a case ready to go for fluid dynamic simulations. To clean up a little bit more, I'm going to actually just remove all of these log files because I know everything worked. You don't have to. You can also make a directory called old log files and just move all of the log files into there. You're not going to need the slurm file or the node file though anymore. Okay, so we are done with meshing.